Hello, hello. How are you guys tonight? Hello, Alicia. Oh, you got your wisdom teeth taken out? Oh, okay, okay, okay. Dang. Okay. Oh my gosh, you gotta tell me, let me know how it goes, how it went, and like if you got hired or not, and how was the experience? Because I think I have to get mine out soon too. It's okay, it's okay. Um, so this is melting. Yeah, I know. And what food have you been eating? Like, are you eating the food that you prepared like weeks ago, months ago? Like when you planned for it? Mashed potatoes. Oh my gosh. Ice cream. Yeah. The cold food really helps with the pain. It like helps numb the pain for sure. Yeah. It was only ice cream, soups, and smoothies. Yes. Oh my gosh. How long did it last? Like the pain, and how long did you have to keep that diet up for, Mark? It still hurts. Oh my gosh. About a week. You got it on Monday. Okay, so you got like maybe a little half a week left until the pain goes away. Yeah. Okay. Um. So four removed at the same time. Oh my gosh. Oh my gosh. Was it the same side or different sides? Like the left, right side? Like I don't know how it works yet. Left and right. Okay. Oh my gosh. Mhm. How long did the procedure last for? Oh yeah, yeah, yeah. You got put to sleep. Okay. Yeah. Actually 45 minutes. Okay, okay. I'll keep that in mind when I get mine out soon. So for today's office hours, we could do 8B, 118B stuff. 8B has their quiz on Friday, so we'll get started with that. So we can start with the questions and we could do 118B and rotate around there. But before we start, I wanna like fix one of like two problems actually that I found when I was rewatching the office hour recordings. Madison, do you remember when we went over the closing the ring technique?
Yes.
Yes, I found a typo that I made in one of the videos, and the star and dot technique too. I found another typo as well.
Oh
Um,
shoot.
yes, let me actually give you a sugar to close, and then I want you to tell me how you would close this sugar, which is hemiacetal formation. And let's see if you got it or not. It's okay if you don't. We could fix it along the way, and I'll let you know what the typo was that I made
Okay.
during the office hours. Okay, so let's say we have this sugar right here. Do you remember what declose looks like without looking at the note card? Like the technique we used for that?
The middle finger technique.
Yeah, the middle finger technique. Right? So let's do that. And I'm gonna
It's
show the
it's
other.
all OH and the middle one's H, right?
Uh-huh. Correct. Yes.
Or
Like
the
this. Like
I guess
the
kind of the middle one.
direction like this, right? Uh-huh.
Yeah.
Like the H is in the middle at the right side. The OH is in the middle of the left side. Right? So this is specifically, is this a D sugar or L sugar? And how do you tell? How do you
This
identify that?
is a L sugar because OH is on the right,
Yeah,
right?
so OH is on the right, which
On
represents
the
a D
bottom.
sugar on the bottom, right?
Oh,
Which is a
okay.
D sugar.
What is but it's like an L is it like an L what's a
Oh, SR or something like that.
yes,
This
yeah.
should be R because this is gonna be priority number one. This is gonna be priority number two. This is gonna be priority number three. This is gonna be priority number four. If we do the rotation in that priority group, it goes
Mhm.
counterclockwise, which is S, right? but it's not actually S. It just looks S because when you think of Fisher projection, right? Think of like a person reaching out its arms for a hug, like that. Like these horizontal lines here are wedges reaching out its
Right.
arms for a hug, and the vertical lines here are dashes going away from you, going away from the page, right? So we see that the lowest priority group here is a wedge. So it's not actually S, it's actually R for this chiral center here, right?
Okay.
But this is going to be classified as a D sugar because the last chiral center here has the alcohol on the right side, right? Okay.
And then if it was on the left, it would be a L sugar.
Yes, correct. If the alcohol was on the left like this,
Mhm.
this would be an L sugar.
Perfect.
Yeah, yeah. Okay. Let's make a 6-membered ring here, alpha and beta enantiomer. Yes, we're gonna get to that now, Mark. Like the alpha beta enantiomer stuff and anomeric carbon stuff. We're gonna close that ring and do that right now. So Madison, let's see how you would do this.
So you would first flip it on its side, correct?
Before we do that though, before we flip it to the side, what's the numbering system? Like what's my number 1 atom and what's my 6 atom here?
Your number 1 starts at the top with the CHO.
Mm-hmm.
And then 2, 3, 4, and then 6 is the CH2OH.
Right, so this...
Or it's the OH on the right.
Yes, it cannot be this CH2OH because that 6 atom here, it cannot be the nucleophile.
Right. And that's when we rotate it, correct?
Correct. That's when we rotate these 3 groups right here before we rotate the thing on its side. We flip the thing on its side. Right, so we're gonna rotate it. Would we rotate it in the clockwise direction, or would we rotate it in the counterclockwise direction if we want the 6th group on the bottom?
I think it was a clockwise.
Clockwise rotation, right? Because we're gonna rotate this OH to where the CH2OH was. We're gonna rotate the CH2OH where the H was, and then the H is gonna rotate to where the OH was, like that. So after rotating all those groups, we're gonna get this right here. So I'm gonna focus on the last chiral center first. OH is at the bottom, CH2OH is on the left side, and H is on the right side. That's the result after that rotation right there. Because I'm rotating this single bond right here and keeping everything on the top here the same, stationary. I keep that still. Right. And this is the result of that, and everything else is just copy and paste now. 1, 2, 3. OH, 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 H, and H like that, which is gonna be 1, 2, 3, 4, 5, 6. And the result, the intention of this rotation of 3 groups here is to make the numbering system go straight down. Before, it wasn't going straight down. At the very end, it tilted to the right a little bit, so we had to rotate these 3 groups to make the numbering system go straight down. And I forgot to tell you guys the trick to remember D-glucose in Fisher projection. So use your right hand, right? And your 4 fingers, index, middle, ring, and pinky finger are going to be these horizontal lines. The direction of where the OH is going to be where your finger is, right? So the index finger, the OH is going to be on the right side. The middle finger is going to be on the left side. The ring and pinky finger is going to be on the right side. So that is how you can remember what D-glucose is. And you can remember that trick and not put it in the note card to save more space, or you could just write in your note card to know what kind of sugar D-glucose is, what it looks like, right? Because you have to know what D-glucose looks like: D-fructose, glyceraldehyde, ribose, and I think galactose or ribose, something like that. Yeah. Yeah. Right. Okay. So now this is when we tilt the sugar to its side. 90 degrees clockwise. Like, it's gonna go clockwise. We're not gonna tilt it counterclockwise, not this direction. We're gonna tilt it this direction right here. Right. And I'm gonna draw out the CHO out like this, right? This CHO right here is an aldehyde, which represents this aldehyde right here. Okay. And this is gonna be 2, 3, 4, 5. Where this is atom 1, this is atom 2, 3, 4, 5, 6. Now, how do you tell what group is up and what group is down?
On the left should be up.
Right.
And the group on the right should be down.
Right. Because if you imagine my arm as the vertical line, and let's focus on this alcohol here on the right side. if I rotate it 90 degrees clockwise, the OH on the right side is going to go down, right? So that means everything on the right, everything here on the right goes down when I rotate it 90 degrees clockwise. Everything on the left right here, if I rotate 90 degrees clockwise, it goes up, right? So 2, we have OH going down, H going down on 3, OH going down on 4, H going down on 5. Now the thing that goes up, 2 is hydrogen, 3 is OH, 4 is H, and now 5 here is not an OH, but it's a CH2OH, like that. Okay, now how would you proceed with the next step to cyclize the ring here? Cyclize the sugar here.
You would essentially like the OH group on the end and the hydrogen connect on the right, on the far right, like 1 and 6, and they form
yes,
a bond.
Yeah, so the oxygen of the 6 here is going to attack the carbonyl carbon of 1. Not the hydrogen, but the carbonyl carbon of 1 right here. Right, and that's going to make a new bond between atom 1 and atom 6, which closes the ring, and we would also have to pop this double bond onto the oxygen like that. Right, now I'm going to draw it in Haworth projection first, which looks like this in this format, where this is atom 1, this is 2, 3, 4, 5, 6. Atom 6 still has its hydrogen and a positive charge, right? But let's say it gets deprotonated to be neutral, like it loses the hydrogen eventually. You're not going to be tested on the mechanism for this, but you will be tested on the procedure on how to close this ring here from linear projection, right? Let's look at 2, 3, 4, 5. At 2, we see OH is going down, so I'm going to make it go down like that. At 3, OH is going up. At 4, OH is going down. At 5, this is when I made the typo. I put OH going up, but what's wrong with that on 5?
It has the C.
The CH2 right there, right?
So,
which you have to draw like that.
Oh, okay.
Or you could write CH2OH if you want, like that, right? But this thing here is the CH2 right there, right? With its 2 invisible hydrogens. Last time when I showed you this, I just made the OH go up, but there's no OH here. It's a CH2OH.
Got it.
Right. Okay. Now at carbon 1 right here, I left that last intentionally because this carbon here is sp2 because that's a double bond. It's flat and planar. So when the oxygen here attacks, it can attack either on the top side or bottom side, giving us the OH on the top or on the bottom, 50-50 chance. Or actually, not exactly 50-50 chance, but we get 2 different products here. One on the top and one on the bottom, like that, at carbon 1. Right, because this carbon 1 here is sp2 flat and planar, like that.
Is that the alpha beta?
Yes, this is the alpha beta enantiomer. How do you tell what's the alpha enantiomer, what's the beta enantiomer? It's okay if you don't remember. Yes.
You want the trans one, or the one where it's like opposite of one another versus the one that's like the one on the left.
Yes, and the thing that we're gonna refer to trans or cis to each other is the alcohol on carbon 1 and the CH2OH on carbon 5, right? We see that the one on the left is cis to each other, the one on the right is trans to each other. This one cis to each other is going to be the beta enantiomer, the one trans to each other is going to be the alpha enantiomer. I think. Wait, let me check just like before we move on. Let's see. Alpha enantiomer. Alpha enantiomer, yeah. The OH and the CH2OH are going to be trans to each other for the alpha enantiomer, right? Carbon 1, right? The carbonyl carbon that was in the sugar, that is called the anomeric carbon. And that might show up in the vocab section. The reason why it's called the anomeric carbon is because when we attack that anomeric carbon, it leads to 2 different enantiomers, the alpha enantiomer and the beta enantiomer. Can't you also tell which is alpha beta based on which way the OH points? So in most cases you can, right? In most cases, if you see the OH going down, a lot of people could say that that's the alpha enantiomer. If you see the OH going up, a lot of people could say that's the beta enantiomer, but that's not always the case. There's some exceptions where if the CH2OH here is going down, instead, like let's say the CH2OH is going down instead. This is going to come from L sugars. Then the OH here going up is going to be the alpha enantiomer, right? And that's because it is trans to the CH2OH. If the CH2OH is down and the OH on one is up, they're trans to each other, which makes them the alpha enantiomer. So that does not follow the rule where OH is up, it's always beta. In most sugars, alcohol will be beta if it's up because most sugars are D sugars. And D sugars, we have the CH2OH going up. But she could give you an L sugar to close, which would not have the CH2OH going up. The CH2OH would go down. And this right here would be the alpha enantiomer now, if she gives you an L sugar instead of a D sugar. Right. So the cis and trans method or procedure is the more 100% for sure way to get the correct answer, instead of the pattern of alcohol on one up, beta, alcohol on carbon one down, alpha. It is true for most cases, but not all cases. Okay. Yes. And do you remember how to convert this to chair from last Ocam class you took? Are you just gonna like draw out the axial and equatorial bonds in your note card and then just like rely on that? That's probably easier to do, huh?
Do you have to do the chair confirmation for this? Like
when you close the ring, I haven't checked the practice quizzes yet, but this is closing the sugar to the hemiacetal, which is this hemiacetal right here, because this carbon has one OH group and one OR group. Okay, Mark said no chairs for this quiz. Okay, so I won't overwhelm you guys, and we won't go over this then. Okay, that's good. That's good. Just worry about the Haworth projection then.
Is there any way you can give us a practice problem for this?
Yes. Let me give you a practice problem for this, but I went over this last time with an aldose. It's gonna be different when we do a the fructose, a ketose, let's say, because ketose can form a 5 or 6 membered ring, and the procedure is gonna be slightly different. So I'm gonna go over that first, give you a practice problem, and then move on to 118 B after this. Okay, so let's do D fructose. CH2OH right here. CH2OH right here. Carbonyl at the second carbon. 1, 2, 3. D fructose is gonna be like this. Okay, so D fructose is a ketohexose, right? Because it's a ketone and it has 6 carbons long in the sugar. 1, 2, 3, 4, 5, 6. But it's a ketone specifically because it's a ketone at carbon 2. An aldose will always have a tro at the top, an aldehyde at the top. That's how you know when you have an aldose. A ketose is when you have a ketone in the second carbon. The official nomenclature for these rings, right, is gonna be like this: 1, 2, 3, 4, 5, 6. So keep that in mind, because what I'm about to show you here is not gonna follow the official nomenclature. It's just my system of how I close the ring, right? Let's say I want to make a 5-membered ring. My carbonyl carbon here is gonna be carbon number 1. This is not the official nomenclature way, but that's my carbon number 1 if I close the ring. I'm gonna go down until I hit my 5th atom, which is the nucleophilic atom, to make the 5-membered ring. This carbon here cannot be number 5. It cannot be number 5 because it has no electrons it could use to attack the electrophilic anomeric carbon 1, carbonyl carbon right there. My number 5 has to be this oxygen right here, so it's the same procedure as we did last time. We're gonna now rotate these 3 groups to make the numbering system go straight down before we tilt the thing 90 degrees clockwise. Right? So as a result of that rotation, we get OH down here, CH2OH on the left, H on the right, and everything else is copy paste. 1, 2, H, H. Okay, now our numbering system is where we want it to be, straight down. 1, 2, 3, 4, 5. Now let's topple it clockwise 90 degrees to get to this configuration here. Right, where this is atom 1 in the numbering system, this is 2, this is 3, this is 4, this is 5 when we close the ring. Everything on the right side is going to go down, everything on the left side is going to go up. So at carbon 2, H is down, 3, OH is down, 4, H is down. At 2, OH is up, 3, H is up, and at 4, CH2OH is up, not OH, but CH2OH. Okay? Now, let's close the ring here. Have this atom 5 attack that carbon, close the ring, and make this 5-membered ring right here. We also gotta pop the double bond to oxygen like that. But you won't be tested on the mechanism of this. You just gonna be tested on how we close the ring here. The template for that 5-membered ring is gonna be like this, where this is atom 1, the anomeric carbon. This is 2, 3, 4, 5. Okay, now let's do 2, 3, 4 first, because that's gonna be the easier one. 2, OH is up, 3, OH is down, 4, it's not OH that's up, but it's CH2OH that's up. So make sure to draw that as CH2OH like that. Don't do the typo that I did, because that would give you some points off if you draw OH instead of CH2OH coming out of that carbon right there. Okay, now carbon 1 was the anomeric carbon, which leads to 2 different anomers. Right, the OH could go down or it could go up. But for this ketose here, we have something else on carbon 1 as well, which is this CH2OH, right? That CH2OH was not there before in the aldose. That CH2OH is going to go on the opposite direction of the OH. So in this left side, because the OH is going down, the CH2OH is going to go up. On the right product, since the OH is going up, the CH2OH is going to go down. So that's the difference between ketose and aldose, and that's how you can tell if a ring comes from a ketose or aldose. At the ring, you see the anomeric carbon has both an OH and CH2OH. You know that this sugar came from a ketose. But if you see that in the ring, the anomeric carbon only has an OH and an invisible hydrogen, you know that came from an aldose, because this invisible hydrogen here is the aldehyde hydrogen, right? That this hydrogen here that is invisible came from this aldehyde hydrogen right here, the trio. But right, this CH2OH right here is the CH2OH of the first carbon on the ketose, like that, right? So that's how you could tell, because there's gonna be some questions that I remember Levin's asking, like, does this come from a ketose or aldose? And that's how you could tell if it comes from a ketose or aldose. Look at the anomeric carbon. If it just has OH and invisible hydrogen, aldose. If it has both OH and CH2OH, ketose. It came from a ketose.
I have a question for this one. Which one would be the alpha and the beta? Is it the same as the other one?
Let's do that. Right.
Hypothesis?
Yes. So based on that, which one would be alpha and beta here?
The left would be alpha and the right would be beta?
Yes, correct. Because the trans one is alpha. The cis one is beta in this case. Right.
Okay, perfect. Thank you.
Okay, of course. Now that was the 5-membered ring. We can make a 6-membered ring for this D-fructose here. So let me copy and paste whatever this thing is, D-fructose, and show you the 6-membered ring here, and I give you a practice problem on closing a ketose to make the 5 or 6-membered ring. Okay, so I'm gonna erase everything here. If I want to make a 6-membered ring, this is gonna be still my atom 1, but now this is gonna be 5, and this is gonna be 6 right here. The numbering system is not straight down, so what we gotta do is we gotta expand this CH2OH out into the Fisher projection. So I'm just gonna copy and paste this whole thing here. Well, this is OH. Copy and paste this whole thing here. And expand out the CH2OH like this. Right, where this whole thing here that I circled in pink, the CH2OH, is this whole thing right here, the CH2OH. This is the C, these are the 2 H's, this is the OH. I just expanded it out to make the numbering system go straight down like that. Does that make sense?
Yes.
Okay, so now we could do everything normally. Flip everything to the side, clockwise, 90 degrees. This is CH2OH, ketose, 1, 2, 3, 4, 1, 2, 3, 4. This is gonna be 1, 2, 3, 4, 5, 6. 2, it's gonna look like this. 3, it's gonna look like this. 4, it's gonna look like this. 5. Now 5 here, we have 2 hydrogens, one up, one down. So when we close the ring to make a 6-membered ring, this is what we get. Now, and there's a common mistake here. A lot of students write the Haworth projection for 6-membered ring like this, but that's not right. The reason why is because when you draw up and down, like let's say this up, down, it's blocked by like that middle bonds right there, right? You can't see what's down or up here very clearly, right? So do not draw that format for a 6-membered ring. Draw this format right here, where it's kind of tilted to the side, like that, right? Where this is atom 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Atom 2, OH is up. Atom 3, OH is down. Atom 4, OH is down. Atom 5, there's 2 hydrogens, right? So we can leave that as invisible. Atom 1, the OH could go down, and the CH2 is up in that case. CH2OH is up in that case. Or it could go, the OH could go up, and the CH2OH can go down. That's the difference at the anomeric carbon, giving us 2 different anomers. 1 alpha, 1 beta. And then everything else, copy paste. Okay. Now in this case, we don't have a CH2OH to refer and have a reference point to make this alpha beta anomer. Now this is when you use the thing, what Mark said, like the direction of the OH. If it's going down, then that's typically considered the alpha anomer. If it's going up, it's considered the beta anomer. But I have like not seen Levin's helix, Nisseri, or Mascal test like if this is the alpha beta anomer, if there's a missing CH2OH here. But if there's a missing CH2OH here, then that's when you use that rule where if OH is down, then it's alpha. If OH is up, then it's beta, right? But don't use that rule for all the cases. Use this rule because they might give you an L sugar instead, which could change things up. Right? But just in case this shows up on the quiz. Down OH would be alpha, up OH would be beta. Any questions on that?
Nope, that makes sense. Thank you.
Yep. Okay, now let me give you a practice problem to close a ring, and I want you to give me the 5 and 6-membered ring, both alpha and beta anomers. So 4 different products in total, alpha and beta for 5-membered ring, alpha and beta for 6-membered ring for this sugar here.
I do have a question though, as far as like when it should be a 5 or 6-membered ring, how would we determine like when to draw each one? If that makes sense. Like on a
Yeah, she will tell you.
Oh, okay.
Yes, like a 5 or 6-membered ring, she will tell you.
Okay.
Yeah. If she doesn't tell you, then you gotta do both, unfortunately. But in like the quizzes that I've seen and the tests that I've seen, she tells you to make the 5-membered ring and 6-membered ring. And it might be tricky because I don't know if you went over this. If you see Pyranos in the name, that's a 5-membered ring. If you see Pyranos in the ring, that's a 6-membered ring. Did you guys all go over this?
Yes.
Vocab? Okay, yeah. So she's gonna be like form alpha D gluco. No, we can't do that. D fructo pyranos, or form beta L fructo pyranos. And what you gotta do is you gotta draw out the sugar in the linear form for memorization from the note card or the tricks that you know, and then draw the D or L sugar of that, and then close the ring, right? So let me actually do that for you. So one problem is that right there. Other problem is gonna be draw beta D fructo pyranos. And this could be the question, and that's all you need, right? Because you have to memorize what fructose is. You have to know what a D sugar is. You have to know what the beta anomer is, and you have to know what pyranos is. Here's another one. Draw alpha L glucopyranos. Okay, so here's 3 problems for you guys to try. First one there, second one here, third one here, right? For this one, the first one, you could draw the alpha beta pyranos, and you could draw the alpha beta pyranos for practice. Okay, but the second one and third one is more specific. Okay.
Awesome.
And now,
thank you.
Yeah. Okay. Yes. So I'll come back at the end of the office hours to check this. Let's move on to 118B. Elysia, Peyton, you guys have any questions or topics you guys want to go over for 118B? Oh, mechanisms with rings? Yes, there's definitely mechanisms with rings. There's intramolecular Friedel-Crafts reactions. So let's do that. Okay. Oh, and the people that just joined, are you guys from 8B? Like Maggie, Sid, Lally, Kelly? Are you guys from 8B? Okay, you guys are in 8B. So what I just did earlier in the session was I went over forming hemiacetals from carbohydrates like alpha, beta, enantiomer, from a glucose, from a fructose like aldose or ketose, and making 5-membered ring or 6-membered ring. And then I gave you guys these 3 practice problems here to try out, which I'm gonna check at the end of the session. So right now I'm just gonna go over 118B stuff. Oh, okay. You're in 118A with Cagley. Do you have a midterm or quiz coming up, Kelly? Or yeah, okay, you do. Okay. What topics do you want to go over the most for 118A? What topic are you struggling with the most here? Spectroscopy using NMR and IR to, okay, that is a pretty big concept, like an HNMR, IR, right? Like, no, like they give you the graphs and you have to like predict the structure from scratch, right? Like with all the information, DOU, and all those things. Or is it just like labeling and matching things for the spectroscopy problem? Okay. The first one, right? Okay. When is your quiz for this one? Tomorrow? Oh shoot. What I could do is I could send you links to videos of like resources that I found useful and my previous office hours that goes over the stuff, especially with my IR chart. Let me find my IR chart for you. This would definitely help you find the functional groups with the IR chart. Where is it? This one right here. This is the IR chart that I came up with, and I always use when I analyze the IR and what functional groups are present, right? But I'll message you. Are you in the Discord, Kelly? Or if you join my school, I could like DM you on that, so it's easier. When I'm free, can I please go over one problem I said on school? Yeah, I'll go over that one problem. Oh, you're not part of the Discord? Okay. Let me send you the link where actually, yeah, you don't have to make a Discord, but you could join this and I'll send you a DM there with the resources and everything for your quiz tomorrow. But I don't have time for today to go over that, but I'll send you the resources here. Okay. Okay, so intramolecular Friedel-Crafts alkylation. AlCO3. So, Elysia, Peyton, do you guys know the Friedel-Crafts reactions, EAS reactions like nitration, sulfonation, and halogenation? Are you guys familiar with that? Oh no. Okay, it's okay. So if I go over this now, it might be a little bit confusing, but let me just go over it and show you the shortcut tips and tricks before I go over the mechanism, right? So what I think about, this is not going to be the exact mechanism. If this is not a mechanism problem, you could do this. If this is a mechanism problem, do not do this, right? This is a warning, do not do this. Do not do this what I'm about to do if this is a mechanism problem, because this is going to be completely wrong for mechanism. But if it's predicted product and you just have to draw the product for credit, this is what you can do to save time on the test. When you see Friedel-Crafts alkylation here, you're going to see a halogen on an R group and a metal catalyst like AlCO3. So what I think on the back of my head is that I'm just going to think that that leaving group is going to leave to form a carbocation on that carbon right there. When that happens, I then stop. And do you remember that one step that we always have to look out for whenever we form a carbocation intermediate? This is from midterm 1 stuff, alkene midterm. Hydride shift or methyl shift, any rearrangement step. Yes, in this case, it's specifically a hydride shift, which we could do that by shifting this hydrogen here over to the left to form a more stable tertiary substituted carbocation. Yes, right? Now, once I do that, I get this new carbocation, which is more stable. Now, this is going to be my electrophile right here. And in intramolecular reactions, the nucleophile is always in the same molecule as the electrophile, and it's always going to form a ring. So my nucleophile here is going to be this carbon, because that's going to form a 1, 2, 3, 4, 5, 6-membered ring, which is the most stable ring-membered we can form, right? And we're just going to close the ring like this. So I drew out that template because I know that that's going to be my 6-membered ring. If this is 1, 2, 3, 4, 5, 6, this is my starred atom. This is my dot atom. This is the new bond that was formed between them right there. Right? So that's just my template. But now I got to copy and paste the decorations. Carbon 6 here has 2 methyl groups. So I got to draw those 2 methyl groups out on carbon 6 like that. If there's like a methyl group on carbon 3, yep, carbon 3, carbon 3, 3, we also got to draw that methyl group on carbon 3. So those are just decorations that you copy and paste. Yeah, you're familiar with this one? That's good. That's good. Okay. Now let's move on to Friedel-Crafts acylation here, which is very similar to alkylation, but it's less problematic. Okay, because there's no rearrangement here. Let's say we have this benzene and we have this reagent right here reacting with AlCl3. So let's do the same thing. The carbonyl carbon here of the acyl group, right? The carbonyl group is the electrophile. This is going to be my nucleophile, which is going to form a 1, 2, 3, 4, 5-membered ring. So when we close the ring, this Cl here goes bye-bye. It disappears. It dissolves in the solution. It leaves in the mechanism. So we won't focus on mechanism here, but this is just predicted product. So draw that benzene ring out. Draw that 5-membered ring template out that we know is going to be formed to make this 1, 2, 3, 4, 5-membered ring, where this is the star, this is the dot, this is the new bond between them, right? That's the template. Everything now is copy and paste. Carbon 3 has the isopropyl group. Carbon 5 has the carbonyl group. So that's intramolecular Friedel-Crafts acylation. So that's the one with the rings. Any questions on that, guys? Before I give you guys practice problems? Pretty easy, easy peasy, lemon squeezy. That's good. That's good. Okay, let me give you some practice, and we'll check it at the end. Let's go. Hopefully, I'll have time for Kelly and Nikki at the end. For Nikki at 118A and UC Berkeley, UC Davis, OChem. Okay, let's see. I want you to.
And then they had to restart the meeting.
You had a question, Peyton? Let's see. 1, 2, 1, 2, 3. Okay, this is gonna be one problem. Another problem is gonna be this right here. Okay, try these two out, and I'll check it at the end. Okay. Hey Nikki.
Hi.
Is it?
I had a few questions.
Mm-hmm.
It was just basically like a few mechanisms that I tried out, but I don't know if I did it correctly.
Yes.
And then also one is about like a lone pair, and if it's like a pi orbital or an sp orbital.
Yes. Yeah. Let's see it.
Send you. Okay.
Yeah.
Okay, I just sent it. The pictures are my mechanisms, and then like if you want to see like the empty, like the blank version of it, I attached the PDF.
Okay. That's good. That's good. Okay. I'm just waiting for the email really quick.
Yeah.
Okay, got it.
There's a few pictures, but the ones that I'm most confused on is it didn't include the number, but it's B. 9B down all the way on the bottom.
Yeah.
8B and then number 1.
Okay. Let me check this out. The first image I see is number 6.
You can skip that one.
Oh, you can skip that one? Okay.
Because I don't think there's enough time, and I think I understand that one for the most
Okay. Sounds good. Number 2.
You can skip that one also.
Okay. Number 8. Yes, number 8?
Yeah.
Okay.
B.
8B. Okay. 8B. The reaction conditions above would potentially lead to a mixture of many products, including the one shown below, which would not involve the carboxylic acid reactant at all. Without drawing a complete curved arrow mechanism, draw the neutral tetrahedral intermediate that would occur in the mechanism leading to the product. So we have this molecule here with an ester, alcohol, and ether. Those are the 3 functional groups present in this reactant, reacting with HCl and heat, which is going to give us this final product right here, which is ether that's still there with its R2. This alcohol here got converted into an ester, and then the ester here got converted to the alcohol. So we flip-flopped here, right? Where the alcohol was is now where the ester is. Where the ester was is now where the alcohol is. Okay. Now, the neutral tetrahedral intermediate is gonna be like, I'm gonna actually draw out the mechanism really quick because that helps me find that answer. Like it says without drawing it, but it definitely helps you find
I was really confused, honestly.
intermediate. Right. Yeah, because like they tell you not to do it, but that's kind of throwing you off because like you don't want to try it at all, but it will help you if you definitely do try out the mechanism to get to this products here. Right. So let's think about this. Okay. This is R1. Interesting. I'm gonna try something because this is an interesting kind of problem, but if it doesn't work, I'll try something else. And then after I try it, I'll explain what this means, Nikki. Protonate that, activate the electrophile, make the strong electrophile. Now once that's activated, this alcohol here does an intramolecular reaction to attack that, push that up there, but that's going to form a ring because this is intramolecular reaction. So that's going to make a 1, 2, 3, 4, 5 membered ring, and we don't have that. in this product. So this is probably not the case. So I'm gonna try something else after. 1, 2, 3, 4, 5. Right? Or this is 1, 2, 3, 4, 5. This 1 here is gonna have positive charge because it has the hydrogen still. This 5 here has the CH2R1. This 4 here is that. This 5 also has an OH like that. Okay. Now, I'm just going to deprotonate this with the Cl- to give me this neutral tetrahedral intermediate right here. So this might be the answer right here, but I'll see. I'll see if this is the answer or not after I complete this mechanism. This is the neutral tetrahedral intermediate for this one. Now, to get to the correct answer here, I'm going to break this bond right here. But to do that, I have to make this into a good leaving group by protonating it, because I want that group to leave and I want to break this bond right here because I want to eventually have a carbonyl right here. And that's going to give me this intermediate right here. So this is the, this is going to be the final answer. But just to complete the mechanism and make it more clear, I'm going to make that into a good leaving group. This alcohol here with a pair of electrons is going to go down, break that off, and give me this product right here. Oh, boom. Oh, this is the intermediate because there's still a positive charge right there. Now this last step here will give us to our product that they gave us right over here. Right, wait, that's R1. R1, yep. Okay, let me double check. Yes, okay. So the answer, Nikki, for the neutral tetrahedral intermediate is going to be this. And let me explain that here.
Okay.
Okay. And this one here looks very wonky because it's a ring with a dash right there, right? So what my thought process was that I tried to do a trans esterification mechanism. Does that sound familiar, Nikki?
Yes.
Trans esterification, right? Where our reactants here, or is this
ester into a second ester?
Yes, ester to second ester with an alcohol, right? Because that alcohol, ROH, creates the second ester with a different OR group.
Okay.
But you notice how the alcohol here and the ester are on the same molecule?
Okay.
The alcohol is the nucleophile, the ester is the electrophile. Every time you see a nucleophile and electrophile on the same molecule, oh my god, which is the pattern that we've been seeing for like the different classes today, for 8B, 118B, and now this class, all intramolecular reactions will always form a ring, right? Which is the ring that we see here. So, do you know the steps of the mechanism for trans esterification, Nikki, or do you want me to walk you through it, like the steps here?
I got the steps that you did. For the most part, I just know that like it's like protonating and then like deprotonating and attacking at the same time.
Yes. And like it's also good to understand why the steps are doing that. Like this alcohol here cannot just randomly attack that ester carbonyl right away, because you know how yesterday we talked about weak and strong electrophiles, like weak and strong nucleophiles. This is a weak nucleophile. This is a weak electrophile. They cannot interact right now by itself. We gotta activate the electrophile by protonating it with the strong acid we have. And once we have this strong electrophile right here, then this weak nucleophile is able to attack that carbon and pop the bond onto oxygen right there, which gives me a ring, right? Because this is the nucleophile that we have, this is the electrophile we have. And the way that I close the ring is I number my number 1 atom, the nucleophile. There's different systems, but this is my system on how to close the ring. My number 1 atom is going to be the nucleophile. And then I go all the way until I reach my electrophile, which is going to indicate that we are going to form a 5-membered ring right there.
Okay.
Right? Now, once I know we're going to make a 5-membered ring, I draw out that template, right? Where I keep track and I be consistent with the atoms here. This is atom 1, 2, 3. Atom 4 here is not a carbon. Atom 4 is an oxygen, which is that oxygen right there. Atom 5 is a carbon. And this is the new bond we made right here between 1 and 5. From that attack. This is the new bond between 1 and 5. That bond was not there before, but it was formed from this attack. Right there.
Okay.
Right. Now, we just attach the decorations. Atom 1 still has its hydrogen, and it's positively charged now because that's 3 bonds. atom 5 used to be double bonded to an oxygen, but we popped the double bond onto the oxygen, creating a single bond OH, like that.
Okay.
Right, and atom 5 is also attached to a CH2R1, which is a CH2R1 right here. So this right here is a tetrahedral intermediate, but it's not neutral. It's positively charged. So to get to the final answer, to get the neutral tetrahedral intermediate, we got to deprotonate it with the base we have, Cl minus, to get to this neutral tetrahedral intermediate answer here.
Okay.
Right, so that's the answer for that part right here. Okay. And then from here, if you want to continue with the mechanism, just to have a better understanding, we want to get to the ester at this point, right? And then the alcohol at this point right here. Which means that I know that since I want an ester, I want a carbon double bond oxygen right here. And I want to break that bond to make this a hydrogen right here, right? So to do that, we have to convert this bad leaving group into a good leaving group. And to do that, we protonate it with the excess acid we have to make it positively charged. And now once that's a good leaving group, I use the pair of electrons on oxygen here to make that double bond to form the carbonyl, carbon double bond oxygen, and break this bond off to create our almost final answer. This like neutral alcohol here, and this ester that is protonated, where the final answer is just to like deprotonate and neutralize the positive charge oxygen.
Okay. Yeah, that all makes sense. I did think of a ring happening at first, but how you explained it, it all makes sense. Thank you.
Yeah, that's good. Yeah, of course. The intramolecular ones are always sneaky, right? Like those reactions are always sneaky because you're used to seeing intermolecular reactions, right? Where the alcohol is separate than the ester, right? And that gives you like a different kind of ester.
Right.
Right.
Okay.
But if the alcohol is on the same molecule as the ester, then that's the intramolecular reaction, right? Okay. Nice. Okay, so I will answer more of your questions tomorrow in tomorrow's office hours. But what I want to do now is I want to check the answers of the 118B ring intramolecular reactions. Wait, what is it? 118B? Yes. 8B and then 118B after. And oh my god, it's like a big pattern today. Like all of the problems I gave today are intramolecular. Okay, Madison, Mark, 118B students, did you guys have the answer for these problems here?
I did the first one with the alpha furanose and pyranose.
Yeah, let's see that.
Working on the bottom two.
Okay, yeah, the bottom two we could check tomorrow. But let's check the first one right now for today.
I forgot what pyranose and furanose meant. Like furanose is 5. And
yes, furanose is 5, and pyranose is 6.
Okay.
Right. So you could think fur as 5, like for 5, and then pyranose like pyridine, which is 6, right there.
Okay.
Yeah.
Perfect.
Okay. You could send your work on the message, and I could check. Today is an intramolecular day.
How did your exams go, Bryant?
I have an exam tomorrow, so I'm gonna be studying for that after this, and one on Friday. So I'm gonna be studying for that after my exam tomorrow. I don't have time to study for the one on Friday right now. But I'm feeling good about the one tomorrow. But I'm just gonna review myself, and then I should be good. I'll let you know how it goes tomorrow. In tomorrow's office hours, how it went.
Yeah, please do.
Yes.
I sent mine.
Oh yeah, Mark also got his as well on the Zoom chat. Let's see. So okay, it's loading on Zoom right now, but let's see Madison's. 5, 6. Whoa, that's interesting. Furanose. Okay. Let's draw Madison's Furanose, which is like this. I think you tried to copy the same format as like the 6-membered ring where the oxygen is at the top right corner, right? But for the 5-membered ring, you can draw the oxygen in the middle like that because we can easily see the up, down, up, down, up, down, up, down like that. But you do not want to draw the oxygen in the middle for 6-membered ring because we cannot easily see the up, down, up, down, up, down, up, down, up, down, right? But in this case, this way, this is also acceptable. You can easily see the up, down, up, down, up, down. So this is also acceptable here. So for alpha, Madison got OH. And at the anomeric carbon, if the OH CH2OH is up, OH has to go down because that's the carbonyl oxygen. OH, OH. And then this is going to go down. So it's going to go down like this. CH2OH. And for the beta anomer, CH2OH. OH, copy and paste, copy and paste. CH2OH down here. OH up here. Okay, so based on this right here, it should be switched. This should be the alpha anomer, and this should be the beta anomer. Because if we look at the anomeric alcohol, that is cis to the CH2OH right here, going down, which is the beta anomer. If we look at the alpha anomer, the anomeric alcohol is trans to the CH2OH, which is the alpha anomer. So this is different than the one that we did, right? Because the one we did was a D sugar. I gave you an L sugar here, which does not follow the rule, like where an up alcohol is beta, right? Because this up alcohol here is alpha, because it's trans to the CH2OH, which is going down, right? Usually the CH2OH goes up for D sugars, but this is an L sugar. So that's why it's switched here, like that. Right, so let me go over the process here.
I think I just forgot to add my OH group on from the carbonyl.
From the carbonyl? Yeah.
Like on
this
the
part here.
CH2OH.
Right,
Yeah.
like this part here.
Because I think if I just added that, then that's when like you flip it. Like you can see why it gets flipped.
Right. You were thinking, yeah, that makes sense, because you were thinking about this and this trans to each other, right? And that's like that's where you got the alpha anomer from.
Yes.
Like the CH2 and CH2OH trans to each other, but you don't look at that. You look at the anomeric alcohol OH and the CH2OH here,
right?
The relationship between them.
Okay.
Yeah. So that's good. Making the mistakes now, so you don't make them during the quiz. You know. Okay. So if I rotate that, I should get this right here. OH, CH2OH, H. Everything else is copy and paste, so I'm just gonna speed run this a little bit. Right. And then 1, 2, 3, and CH. Whoa. That is incorrect. CH2OH is supposed to be on the right side, and H is supposed to be on the left side. Okay. This is up, down. Okay, that's gonna give us either this anomer, this is up, this is down, this is down, like that, and that's the alpha anomer, and that is what Mark got. So Mark, for your 5-membered rings, everything else is correct, like 1, 2, 3, 4, right? But the 5th atom, or like actually the 4th atom, the CH2OH on the left side, the top left side, it should be going down because this is an L sugar, right? That would be right if this was a D sugar, but this is an L sugar, so the CH2OH should be going down.
Yeah, I just noticed as you were drawing it when you were flipping it, so.
Right, because in most practice problems that you've seen, it's usually D sugars, right? Like the most practices you've seen, it's usually CH2OH going up, right? And that's like where you follow the pattern. But this is an exception where it doesn't follow the pattern. That's good. Right. Okay. And the other answer is gonna be like this right here. OH, 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 CH2OH. Yeah. Okay. So let's move on. Okay, that's the 5-membered ring. Let me do the 6-membered ring here really quick. Did you guys get the 6-membered ring for this one as well? Oh yeah, Madison did. Let me check the Madison's answer here. Okay, so now this is 5, this is 6. We expand that out to have this CH2OH like this. Everything else is copy and paste. 1, 2, OH, 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 H, H, H. Now this is 1, 2, 3, 4, 5, 6. Okay, now I'm not gonna do the tilt thing because I already know everything on the right is down, everything on the left is up. So to draw that 6-membered ring out like this, I could have on this carbon OH is up, this carbon OH is down, this carbon OH is up, right? So that's copy and paste for this other product here. And then for this one could go down, this one could go up, this one could go up, this one could go down, right? And then now there's nothing here that's missing. So we do that rule where OH down, alpha, OH up, beta. Okay, let's check Madison's. OH up, beta, yep. OH down, alpha, yes. And her alcohol locations, correct. Yeah, you got it, Madison. For this one, the 6-membered ring. Yes.
1.
No, you got 2.
Or 2, technically.
Alpha, beta, yes. Let's go.
5 hours of studying for that one.
Oh my gosh. That's good. We celebrate the wins, even if it's small. Anyway, all wins.
Yes.
Yes. Okay. Let's do 118B. Elysia, let me check your answer. Okay. Well, where is it? Right here. Okay. Let's see, Elysia's. Crossing your fingers. Let's see it. Okay. Oh boy, Elysia, there's no bromine here. That's a methyl group. Right, but what you're gonna do is you're gonna kick that out in the back of your mind, and you're gonna form a carbocation right here. But now this is the tricky step. Let's say this is my nucleophile. Would you want to do a hydride shift to shift the carbocation at A or at B? Which one would you want to do to form the more stable ring? Which one would give you the more stable ring if this is my nucleophile? So if A is the electrophile, right? Let's count how many carbons would that be in the ring. That would be 1, 2, 3 carbon ring. If you choose B, that would be a 1, 2, 3, 4, 5-membered ring. What's more stable, 3-membered ring or 5-membered ring? Five-membered ring, right? Because there's less ring strain, less bond angle strain. So we want to do the hydride shift on B, right? Even though both are tertiary, B would give us the carbocation that leads to the more stable ring, the 5-membered ring. Less ring strain, less bond angle strain, right? I don't know if you remember those terms, Kelly, from 118A, but that's like, I don't know, that's like pretty recent for you. We're just going to be in the final, Kelly. And that's going to be the star. That's going to be the dot to form this 5-membered ring. 1, 2, 3, 4, 5 to make this ring right here. Let's draw that 5-membered ring template. That's just a template because I know that this is going to be 1, 2, 3, 4, 5. Now I just copy and paste the decorations. 3 has a methyl and 5 has 2 methyls like that. Yeah, let's not go with A. A is terrible. That's very sneaky right there. A is very sneaky. Don't go with A. Okay, that's good. Wait, let me see what you did here. Actually, you got, yeah, well, you got the 2 methyls here, and if you like converted this bromine that you thought was a bromine into a methyl, that would be correct. But get rid of that bromine in the middle because that bromine leaves in the mechanism. Like there's no bromine here in the middle, right there. Yeah. Okay, let's look at your next one here. Okay, so this is my electrophile. This is my nucleophile. That forms a 1, 2, 3, 4, 5, 6-membered ring. So let's draw that template out with the 6-membered ring. Yes, Cl leaves here. Nice. Cl goes bye-bye. It leaves. Right, it gets kicked out, gets the boot. just gonna form the 6-member ring right here. That's gonna be 1, 2, 3, 4, 5, 6. Yep. 3 is ethyl. 4 methyl. 5 nothing. 6 carbonyl. Right, and that's a carbonyl, Alicia. The carbon double bond oxygen, not carbon double bond carbon. Right, it's a carbon double bond oxygen right there. But everything else you got is correct. Nice, you got it. Like if this was predicted product, that is right. It looks wrong, but it's right. Just don't forget that oxygen right there. Yeah, no worries. Oh my gosh, you changed your notes format. You used like a black grid now and white ink. Yeah, that's good. Okay, so I'm gonna end office hours here with, let's say, Kelly's any questions about spectroscopy, HNMR, IR for your quiz tomorrow for CAGLI 118A, Kelly. Sorry, I didn't have time to go over like specific problems, but I wish I had time to do that. Yeah, of course. Maggie. Let's go with thing I couldn't. Okay, so what you could do is you could message me here and I could send you the resources after. There you go. Okay. Yes, so this is the end of the office hours. You guys have exams this week? Like a lot of exams? A lot of people have exams this week. They've been telling me like they have exams tomorrow, on Friday, quizzes that time too. Yes. Thank you.
Thank you.
Yep, of course. Good night, guys. Bye. Bye.